Welcome back everyone to section number 5. This video is talking about some additional properties, in particular for nice symmetric functions, right? So if we have nice symmetric functions, the claim is sometimes we can make these definite integrals go a bit faster. So let's go ahead, I'll give you the theorems and then we'll actually use them in a couple examples. All right, so recall, again, f is called even if f of negative x is equal to f of x. So that is, we have symmetry about the y-axis. F is called odd if f of negative x is equal to negative f of x. That is, we have some rotation symmetry about the origin. Okay, so if we have either an even or an odd function, again, the claim is that some definite integrals we can actually evaluate a little bit faster. And the way we do this, right, so part A, if we have an even function, and suppose that we are integrating from negative some value, a, to some other value, a. Well, then in this case, this will be the same as if you just integrated from 0 to a for our function, and then you doubled it, right? So we did 2 times the integral from 0 to a. So again, let's go ahead and maybe draw a picture and convince ourselves why this might be the case. So if we have an even function, again, there's kind of some nice symmetry about the y-axis. So I know if I have something that looks like this over here, because it's symmetric, I have to have maybe like this over here. Okay, and so now if I'm integrating from maybe negative a to a, and I want to calculate out all of this area here. So all of this here plus all of this here. There we go. The claim is because it's symmetric, and maybe I didn't do a great job actually sketching this out, but if you want to calculate all of that purple area, that's the same thing as calculating up maybe this orange area here and doubling it, because again, there's this nice symmetry going on. Okay, so this is kind of nifty. Sometimes I see this saving, maybe us one step or so and actually evaluating out some definite integrals. But the second one here is much more powerful. So if we have f is some odd function, again, we're integrating from negative a to a for an odd function, this is just equal to 0. So this actually will allow us to evaluate out some integrals that we normally wouldn't be able to evaluate because of this property, that if you have an odd function, right, this integral from negative a to a of f of x dx will be equal to 0. So let's again maybe just sketch out a picture and see why this might be true, convince ourselves here. So if I have an odd function, right, so there's some rotation symmetry about the origin. Maybe I have something like this. So in that case, because there's this rotational symmetry, it's going to look something like so. So that way when I rotate it about the origin, right, by 180 degrees, it'll look kind of the same. And again, kind of if you were to count up all this area over here, maybe let me specify, right? So this will be for negative a to a. So adding up all this area here and all of this area down here, well, remember, because this is net area, the stuff underneath the x-axis gets counted negatively. Right? So the claim is these two areas perfectly cancel each other out. So it really does matter, right, that these are from negative a to a. Right? If you have, for instance, from negative 3 to 4 or something like this, that won't work. Right? It has to be like negative 3 to 3 or negative 4 to 4. Right? They have to be kind of the same, just one's the negative or the opposite of the other. All right, so let's go ahead and see how we can use this. I have a couple examples for us here. So, okay, this is a pretty complicated one. Remember, kind of our main strength for finding antiderivatives, right? After we stare at this for a second, we identify that it's not geometric, or, right, maybe it's something that we can't really find the antiderivative of very quickly, right? We're going to use our u substitution. So I'm going to use my u substitution here, and this one, it requires a little bit of thought, a little bit of kind of guessing and checking, but after a little while, hopefully we will get u is equal to tangent of x. And the reason why is, well, tangent is inside of the squaring function, right, that this is being squared, and we see its derivative, right, the derivative of tangent is hanging out here, right, so when I take the derivative of u, the derivative of tangent, I'm going to get secant squared x dx. So, right, I'll be able to go ahead and trade in all of this stuff here for a du, all of this stuff here for a du. So let's go ahead and maybe start evaluating here, or start swapping out. So let's see, u is tangent, so this is going to be tangent squared, or u squared, and then everywhere I see the secant squared of x dx, I'm going to go ahead and swap it in for a du. Now we need to go ahead and change our bounds, right? So when x is equal to negative pi over 4, what is the corresponding u value, right? What kind of limit of integration should I put here? Well, if I plug in negative pi over 4 into tangent, I get out negative 1. So this is going to be negative 1. If I was to plug in positive pi over 4, that is my upper bound, then plug that in again to my tangent function. Tangent of pi over 4 is equal to 1. So this is going to be from negative 1 to 1. And now we really see, right, first of all, u squared is kind of the classic even function. And we're going from some negative a to a, right? These are the same values, it's just one's negative. So this is a classic even function. And so if we'd like to use this property, we can go ahead and write down that this will be equal to 2 times the integral from 0 to 1 of u squared du. All right, we go ahead and just trade that in 2 times the integral from 0 to a, in this case 0 to 1, of our function. All right, now let's go ahead and evaluate this. So this is going to be u cubed times 1/3. We're going to evaluate that from 0 to 1. So this is going to be 2/3, and that's going to be 1 minus 0. So altogether, the answer is 2/3. So again, like I mentioned, this one sometimes saves us like one step or so. Maybe this evaluation was a little bit easier. I like plugging in 0 rather plugging in negative 1, right, which is what I would have normally had to do. So it does make it go a little bit faster, but again, this property is just okay. Now the next property, right, for this odd stuff, this is really where a lot of power comes in, right? So okay, looking at this one right here, so the claim is, looking at this, I would be able to integrate 1, and I would be able to integrate x, okay. But when it comes to this x squared tangent of x, that's difficult, right? Even with my u substitution and stuff, the claim is I could spend, an hour or so trying this thing, and nothing would work. There's not a good u substitution that we can actually make in this case. But I notice, right, that we do have negative pi over 4 to pi over 4, so I'm hoping, right, if this is an odd function, then I know that this will just integrate out to be 0, and then maybe I don't have to actually find the antiderivative. And so let's go ahead and verify that this is actually an odd function. So again, I'm going to plug in negative x everywhere I see an x. So this is going to be negative x squared times tangent of negative x. And I'm going to simplify this down, and again, I hope it's going to be odd, so I hope I get negative the original, right? Negative of x squared tangent of x. So let's see, already I see negative x times negative x, that is going to be x squared. And now tangent of negative x, this is the same thing as sine of negative x divided by cosine of negative x. Sine is kind of a classic odd function, and cosine is a classic even function. So let's see. For odd functions, we know that we can kind of just strip out this negative sign. So I have negative sine of x. And for even functions, you can basically just forget about it, right? You just get cosine of x. Because again, for even functions, f of negative x is equal to f of x. And for odd functions, f of negative x is equal to negative f of x. Okay, so now we can go ahead and take that negative sign and move it out front maybe. And so let's see, negative x squared and sine of x over cosine of x, that's equal to tangent of x. So this is equal to, right, when I plug in a negative x, this is equal to negative the original function. So again, our original function was x squared tangent of x. This is the negative of that. So this is odd. Okay, so now let's go ahead and use one of our properties of definite integrals here that says that you can go ahead and distribute these definite integrals kind of to each piece if you'd like. So I'm going to go ahead and do the integral from negative pi over 4 to pi over 4 of 1 dx plus the integral from negative pi over 4 to pi over 4 of x dx plus the integral from negative pi over 4 to pi over 4 of our complicated function, our x squared tangent of x dx. And now we know, because it is odd, right, we're using this theorem back here, because this is odd, even though it's quite complicated and I don't know what the antiderivative is, right, I don't really have a good way to solve this, I do know that this is going to evaluate out to be 0. And in fact, x itself is another kind of classic odd function, right? It's x to the first power. So in this case, it is also odd. We will also get 0 in this case. Now this one we could evaluate out, and you can just verify that we would get 0. But this is a nifty trick. So really the only thing that I need to evaluate is the integral from negative pi over 4 to pi over 4 of 1. So if I take the antiderivative of this, I'm going to get x, and we evaluate that from negative pi over 4 to pi over 4. So let's see, I plug in pi over 4, and then I subtract away a negative pi over 4. So this is really subtracting a negative is adding. So this is going to be pi over 2 altogether. So, and in fact, if we wanted to, we could even use the first part of that theorem, right? Because 1 is actually an even function. So if you wanted to, you could use that and make it even, maybe one step easier. But again, kind of this second part of this theorem, that if you have odd functions, then their definite integral from negative a to a, equals 0. This is very strong because, again, I had no idea how to find the antiderivative of x squared tangent x, but luckily with this theorem, I don't need to. All right, that's the last example for this video, and that's it for 4.5. I'll see you guys next time.